On December 19th, as the interstellar object, 3I Atlas makes its closest approach. We are listening for a signal. Conventional fear suggests a declaration of war. However, based on the dark forest hypothesis, the most terrifying scientific outcome is not a threat, but a warning, a command to cease all transmissions immediately. In a universe filled with silent predators, our radio waves are not a sign of intelligence, but a target. Today, we analyze why a command for silence implies a danger far greater than any invasion fleet, and examine the physics behind survival through total radio silence. If you value objective scientific analysis, please hit like and subscribe to support the channel. Let's examine the data to understand the significance of 3I Atlas. We must first look at the context of interstellar objects. These are phenomena so new to our scientific catalog that we are still refining the nomenclature. Before the year 2017, humanity had never confirmed a single visitor from outside our solar system. Then came Oumuamua, a tumbling, cigar-shaped object that passed through our neighborhood with high velocity, offering us only a fleeting glimpse. Then came 2I Borisov, a comet that, chemically speaking, looked almost disappointingly normal. And now, we have 3I Atlas. This object refuses to fit neatly into either category. Ground-based telescopes have been tracking it for months. Spectral analysis, the study of light interaction with matter, shows chemical signatures consistent with cometary ice and rock. On the surface, this appears mundane. The European Space Agency's XMM Newton Observatory detected X-ray emissions as the object began interacting with the solar wind. Again, this is consistent with standard cometary behavior. When charged particles from the Sun collide with the neutral gases streaming off a comet's surface, a process called charge exchange occurs, generating X-rays. It is basic plasma physics. However, the psychological impact of these readings is different. X-rays sound dangerous. To the layperson, they sound like radiation warnings, something to evacuate from. But what makes 3I Atlas distinct is not the emissions themselves, but the duration of our observation. Previous interstellar visitors moved with such velocity relative to the Sun that by the time we trained our most sensitive instruments on them, they were already on their outbound trajectory, fading into the dark. 3I Atlas is different. Its trajectory brought it into our solar system at a specific angle that has allowed for months of continuous observation. We have had time to scrutinize every flicker of luminosity, every shift in chemical composition, and every minute deviation in its path. And with that extended observation time comes a cognitive danger known as pattern recognition. Velocity is the primary variable here. 3I Atlas is moving faster than anything gravitationally bound to our Sun should move. This hyperbolic excess velocity is the defining characteristic of an interstellar object. It indicates that the object is not just passing through, it is escaping the Sun's gravity well entirely. But the speed raises questions. If an object is moving too fast, we must ask what kind of astrophysical event could fling a rock across light years of empty space. If it is moving too slowly, or if its acceleration changes without a clear gravitational cause, we are forced to consider if it is maneuvering. Let us be scientifically precise. No artificial signals have been detected from 3I Atlas. There have been no narrowband radio transmissions, no optical laser pulses, and no mathematical sequences beamed in our direction. The object is behaving exactly as a comet should, outgassing, tumbling, and reflecting sunlight based on its rotation and albedo. If you choose to classify this as a purely natural phenomenon, you have every scientific justification to do so. But in the search for extraterrestrial intelligence, the absence of a signal is not the same as the absence of information. There is a question that circulates in observatories, often unspoken in peer-reviewed journals. If we did receive a message, what kind would be the worst? The public assumes it is an ultimatum, a countdown to invasion. But that scenario, while terrifying, provides data. It tells us who is out there. It tells us what they want. It provides an enemy with understandable intentions. The truly frightening messages are the ones that do not resolve anything. These are messages that leave us staring at data we cannot interpret, listening to a silence that feels deliberate, or watching an object that obeys the laws of physics but still feels wrong. Ambiguity is corrosive to the scientific process. It turns every observation into a question mark. It forces us to second-guess our instruments, our standard models, and our interpretation of reality. We can categorize this terror into a hierarchy of 3 levels. These are 3 types of hypothetical transmissions that escalate in horror, not because they become more hostile, but because they introduce more uncertainty. The first level is confusion. This would be a message that mirrors our own broadcasts back at us, a signal that is statistically impossible to occur naturally, but contains no new information, only a reflection of our own noise. The second level is distress. This is a message that frames the visitor not as an explorer or a conqueror, but as a refugee. It implies flight from a threat we cannot see and do not understand. And the third level, the one that aligns with the dark forest theory and keeps SETI researchers awake, is corrective. This is a message that is neither a greeting nor a threat. It is a simple instruction: stop broadcasting. If the scariest message we receive is not hostile, but corrective, the implications are profound. It means someone out there knows something we do not. It means our presence, our radio leakage, our radar pings, our television broadcasts has been noticed, and it means that being noticed might be the most dangerous thing the human species has ever done. Consider the logic of a corrective message. A civilization advanced enough to cross the interstellar void, sophisticated enough to locate a developing species like ours among billions of star systems, does not send a greeting. It does not request cultural exchange. It does not threaten conquest. Instead, it tells us to be quiet. That single instruction carries more weight than any weapon because it suggests the universe is not empty. It suggests the universe is full. But it is full of civilizations that have learned a hard lesson: survival depends on silence. Meanwhile, Earth has been shouting into the void for over a century. 3I Atlas reaches its perihelion, its closest point to the Sun, soon, and its closest approach to Earth on December 19th. Observatories around the world are preparing for maximum observation windows. Amateur astronomers are training their telescopes on coordinates that are updated daily. Data will flood in regardless of our readiness. Whether the object is a chunk of ice, a derelict probe, or a messenger, we will be watching. And the unsettling possibility remains that it has been watching back. The critical question isn't necessarily whether we will receive a message in the future. The question is whether we have already received one and simply haven't recognized it yet. The most dangerous messages are not the ones that announce themselves on a specific frequency. They are the ones hiding in plain sight within the data, waiting for us to understand the pattern. And if we do understand, if the data suddenly clicks into place and reveals a reality we were not prepared for, humanity will face a choice no civilization should have to make. Do we listen to the warning, or do we keep broadcasting into the dark? hoping that whoever told us to be quiet was wrong about what is out there hunting for noise. This brings us to the core of the scientific challenge differentiating signal from noise. Why would we even expect a message in the first place when astronomers point their instruments at an object like 3I Atlas? They are not listening for radio signals in the traditional sense employed by SETI. They are observing the behavior of light. They are measuring brightness over time to create a light curve. They are splitting that light into its component colors through spectroscopy to identify the chemical fingerprints of elements like hydrogen, carbon, and oxygen. They are analyzing polarization, which reveals the alignment of light waves and provides clues about the surface texture or the atmosphere scattering them. And they are monitoring for non-gravitational acceleration, tiny changes in velocity that cannot be explained by the sun's gravity alone. None of these measurements are designed to detect intelligence. They are designed to determine composition, trajectory, and origin. This is why we should not expect a radio hello. If 3I Atlas intended to announce itself clearly, it would need to emit electromagnetic radiation in patterns that violate natural laws. It would need to produce a signal so obviously artificial that even the most skeptical astrophysicist would have to concede. But that is not the scenario we are facing. Instead, we are dealing with the concept of accidental messaging. These are emissions or behaviors that are not intended as communication but still carry information. Consider an analogy. When you walk across a sandy floor, you leave footprints. You did not intend to tell a story with those footprints. But a forensic analyst examining them later could infer your weight, your gait, your speed, and even whether you were running or walking. The object does not need to be trying to communicate for us to receive a message. It simply needs to exist in a way that creates anomalous patterns. History is replete with false alarms in this domain. In 1967, astronomers detected repeating radio pulses from deep space. These pulses were so regular, so precise, occurring every 1.33 seconds that the source was briefly labeled LGM-1, standing for Little Green Men 1. It seemed impossible for nature to produce such a metronomic signal. However, further analysis revealed the source to be a pulsar, a rapidly spinning neutron star with magnetic fields so intense they beam radiation like a cosmic lighthouse. It was natural, predictable, and explained by physics. But for a brief moment, humanity thought we had found them. Early SETI programs faced similar disappointments. Signals that appeared artificial turned out to be interference from passing satellites, military radar installations, or even faulty microwave ovens in the observatory break room. The universe is full of objects that produce patterns. Water masers in star-forming regions emit microwave radiation at specific frequencies. Quasars flicker. Magnetars burst. The cosmos is noisy in ways that have nothing to do with intelligence. This is why pattern recognition is dangerous. It is unavoidable. Our brains are wired to find order in chaos. And when we look at an anomaly like 3I Atlas, we must be rigorously careful not to see a message where there is only rock and ice. Yet, the possibility of a corrective message, a warning to be silent, remains the shadow hanging over every observation. We see faces in clouds, hear voices in white noise, and assign meaning to coincidences. This cognitive bias pareidolia kept our ancestors alive by helping them spot predators in the underbrush. But in the context of astrophysics, it makes us prone to a dangerous error, seeing signals where none exist. And now, we have automated that bias. Artificial intelligence systems flag anomalies faster than humans can contextualize them. Machine learning models trained to find outliers will inevitably find outliers, whether those data points are meaningful or merely statistical noise. The psychological hazard here is that humans interpret structure as intent. If something looks organized, we assume someone organized it. If something repeats, we assume it is trying to communicate. This assumption works in human contexts, but it breaks down when applied to the universe. A crystal has structure. A spiral galaxy has structure. Neither was designed. So, what would constitute a real message from 3I Atlas? Not necessarily intent, but information that fundamentally changes what we know. A genuine message might look like data behaving incorrectly. It could be a light curve that defies every cometary model. A chemical composition that thermodynamics suggests shouldn't exist outside a laboratory. Or a trajectory that requires forces we cannot account for. The message would not announce itself. It would simply sit there in the numbers, waiting for someone to notice that the equation does not balance. This is where the scientific process becomes uncomfortable. If the numbers do not add up, you have two options. Option 1, your models are incomplete. This is the safe answer. The one that maintains the natural order, you recalibrate. Account for missing variables. And eventually, the anomaly resolves into something explicable. Option 2, the numbers do not add up because the data is being manipulated. You are not observing natural phenomena. You are observing a signal disguised as natural phenomena. And then there is the possibility that terrifies information theorists more than anything else: the data reflects us. What if the message isn't about the object at all? What if it is about what the object has observed about us, our broadcasts, our transmissions, our century of electromagnetic noise bleeding into space? What if 3I Atlas isn't sending a message, but returning one? What if it is showing us our own reflection, distorted by distance and time, proving that someone has been listening all along? That would change everything. It would not just mean we are not alone. It would mean we have been studied, catalogued, and understood in ways we do not understand ourselves. And if something out there knows us, that well knows what we broadcast, when and how, then their silence is not just a preference. It might be a survival strategy they are trying to teach us. This brings us to the first level of cosmic terror: confusion. A message at this level contains no threat, no welcome, and no explanation. It is simply a mirror held up to show us what we look like from the outside. And that reflection is more disturbing than any monster could ever be. Imagine this scenario. Astronomers analyzing data from 3I Atlas notice something strange. The object's outgassing plumes, jets of gas and dust, vary in ways that correlate statistically with Earth's radio transmissions. The correlation is not perfect. It does not scream artificial intelligence, but it is consistently above the noise floor. Appearing in multiple independent datasets, it is enough that you cannot dismiss it as coincidence. The object appears to be echoing us. This is the confusion level, a message that contains no new information but proves prolonged observation. It is not hostile. It is not even communicative in the traditional sense. It is demonstrative. It says, "I know you are there. I have been listening. Here is the proof." Theoretically, this could occur naturally. Electromagnetic radiation from Earth has been leaking into space for over a century. Radio waves from early broadcasts are now more than 100 light-years away, propagating outward in an expanding sphere. If an interstellar object passed through that sphere, it could conceivably interact with that radiation. Interstellar dust and plasma can act as natural reflectors. The physics isn't impossible, but the implications are devastating. Because if the correlation is real, it requires that something was positioned to observe us not just recently, but for decades. It requires that whatever is doing the observing has been paying attention in silence, cataloging our transmissions without ever responding. This is the oldest nightmare of the search for extraterrestrial intelligence: SETI passive surveillance. Being watched is fundamentally different from being contacted. Contact implies a relationship, perhaps even an adversarial one. Surveillance implies asymmetry. It means someone has been studying you while you remained ignorant of their presence. It means they know more about you than you know about them. Most disturbingly, it means they have been making decisions about whether to reveal themselves. And so far, the decision has been no N. The idea of non-interactive intelligence unsettles our anthropocentric view of the universe. We assume that if someone is out there, they would want to talk. But what if observation is enough? What if they are cataloging civilizations the way we catalog stars? Noting our existence in some vast database without any intention of engagement, we become specimens, objects of study, data points. The mirror message concept flips the discovery narrative on its head. Usually, when we search for aliens, we are trying to learn about them. But a mirror message forces us to learn about ourselves, how we appear from the outside, what our electromagnetic signature looks like from a distance, what patterns we create without meaning to. Scholars of Earth might study our transmissions the way we study ancient texts, parsing them for information about our technology, our conflicts, our entertainment, and our fears. They could know more about human civilization from our leakage than most humans know about their own history. And yet, they have said nothing. This silence is the terrifying variable. If they are watching and not contacting, what does that tell you about their assessment of us? Are we not interesting enough, not advanced enough, too dangerous, or perhaps too primitive? The lack of response is itself a message. But we cannot decode it because we do not know the criteria they are using. This level causes paralysis, not panic. Panic requires a clear threat. Paralysis comes from not knowing what to do with information that changes everything but demands nothing. Do you respond? Do you stay silent? Do you assume the observation is ongoing or was a one-time event? Every choice feels like a gamble because we lack context. Some researchers would argue for an immediate response, send a deliberate message back, acknowledge that we have noticed, and attempt to open a dialogue. Others would argue for extreme caution. If they haven't contacted us, maybe there is a reason. Maybe response is dangerous. Maybe the smart play is to act like we didn't notice and wait. But both positions assume we understand what is happening, and we don't. The mirror message doesn't tell us anything except that we've been seen. It doesn't explain why. It doesn't explain by whom. It just confirms that the assumption we've operated under for centuries, that we are alone and unobserved in the cosmos, is false. Someone has been paying attention, and that changes the entire game. But confusion is only the first level. If the mirroring is intentional, it raises the question, why reveal surveillance unless you want something, unless you are trying to send a warning, unless the act of observation itself is supposed to tell us something we are not grasping? This leads to the second possibility. The object isn't observing us. It's fleeing, and it wants us to know, because whatever it is running from might be coming for us next. This brings us to the scientific divide: natural versus artificial interpretations. The official position is clear. The NASA Near-Earth Object Program classifies 3I Atlas as a comet. The European Space Agency's reports describe outgassing consistent with the sublimation of volatile ices. The International Astronomical Union lists it in the same catalog as every other minor body we have ever tracked. There is no controversy. There is no debate. The object is natural. Science defaults to natural explanations for good reason. Invoking the unknown without exhausting the known is lazy thinking. Every unexplained phenomenon in history, lightning, earthquakes, comets that was once attributed to gods or omens, turned out to be weather. geology, and orbital mechanics. Assuming otherwise wastes time and credibility. But there are unresolved anomalies, small ones. The kind that fit within the error bars of measurement, but still make you look twice. Polarization data from certain observation windows does not quite match standard cometary models. It is close enough that you can invoke dust, grain, alignment, or unusual surface textures to explain it. But it is off enough that it gets flagged in internal reviews. Compositional oddities exist. 2. The ratio of carbon dioxide to water vapor is within the range of known comets. But on the extreme end, not impossible. Just rare. History teaches us that natural does not always mean expected. When pulsars were first detected, they defied all existing models of stellar physics. The idea of an object spinning hundreds of times per second seemed absurd until we understood neutron stars. When fast radio bursts started appearing in telescope data, they violated assumptions about what could produce that much energy in that little time. Now we have partial explanations, though the full picture remains unclear. This history serves as a reminder that nature surprises us constantly. The boundary between rigorous science and pure speculation is not a solid wall, it is a gradient. At one end, you have peer-reviewed observations data that replicates across multiple instruments and observatories. At the other end, you have hypotheses that cannot be tested with current technology. But in between lies the gray zone, the space where scientists ask questions without claiming to have answers. This is where papers are published with titles containing phrases like possible interpretations and alternative scenarios. Asking these questions is not conspiracy, it is methodology. Science progresses by challenging existing models, by finding edge cases that do not fit, and by admitting when we do not know something. The problem arises when speculation is stripped of its caveats and presented to the public as fact. When a scientist says, "We cannot rule out the possibility," and a headline reads, "Scientists confirm." The telephone game between research and public understanding introduces distortion at every step. True scientific skepticism looks like this, acknowledging that most anomalies resolve into natural phenomena once better data is acquired, while remaining open to the possibility that some do not. Sensationalism looks like this, treating every unexplained data point as evidence of intelligence while ignoring all the explained data points that surround it. One approach is intellectually honest, the other is profitable. The real frontier lies in unknown natural processes. The universe operates on scales and in conditions we cannot replicate in laboratories. We have never seen an interstellar comet up close. We have never sampled material that formed in a different stellar system. Every assumption we make about what is normal comes from a sample size of our own solar system. 3I Atlas could be doing something perfectly natural that we simply have never witnessed before. The challenge lies in distinguishing between "we don't understand this yet" and "this cannot be explained naturally." Those phrases sound similar, but they have profoundly different implications. The first means we need more data. The second means we need to reconsider fundamental assumptions about what is possible. Scientists are trained to exhaust the first option before even considering the second. But exhausting natural explanations takes time. You need observations across multiple wavelengths. You need spectroscopic analysis with high signal-to-noise ratios. You need trajectory data refined over weeks or months. You need computer models that account for every known gravitational and non-gravitational force. Only after all of that fails to explain what you are seeing can you legitimately say the phenomenon is anomalous. And even then, you have to consider observer error, instrumental artifacts, and mathematical mistakes before invoking anything exotic. Uncertainty is fuel for narrative fear. When you do not have a complete explanation, the human brain fills in the gaps. And human brains are terrible at filling gaps with boring possibilities. We do not imagine unusual but natural dust grain alignment. We imagine surveillance. We imagine intent. We imagine danger. Because stories about mundane misunderstandings do not keep you awake at night. Social media accelerates this process. An astronomer mentions an unexplained data point in a conference presentation. Someone live tweets it. The tweet gets shared with added speculation. By the time it reaches the general public, it has transformed from an anomaly requiring further study into proof of alien technology. The researcher then has to spend valuable time issuing corrections instead of doing research. This creates a perverse incentive structure. Scientists who refuse to speculate publicly get ignored. Scientists who speculate carefully get misquoted. Scientists who speculate carelessly get amplified. The ones who benefit most are often the ones willing to make the boldest claims with the least evidence. That is exactly backward from how science should work. But when enough anomalies cluster in one place, when the list of things that need explaining grows longer than the list of things already explained, curiosity mutates into suspicion. You start wondering if the lack of a clear explanation is itself information. You start asking not just what the object is, but what it is doing here, and why now. Why this particular trajectory at this particular time? Is it coincidence or something else? This brings us to the controversy surrounding modern astronomical speculation. Speculation is no longer just for the fringe. The conversation shifted fundamentally after Oumuamua. Before 2017, suggesting that an interstellar object might be artificial was career suicide for a serious astronomer. After the Oumuamua flyby, it became a discussable hypothesis, not a dominant one. Not one that most scientists endorse, but one that appears in papers published by reputable institutions. Avi Loeb, the former chair of Harvard's astronomy department, proposed that Oumuamua could be a light sail, a thin reflective surface pushed by solar radiation pressure. His reasoning focused on the object's non-gravitational acceleration and its unusual shape. Mainstream astronomers pushed back, offering alternative explanations involving hydrogen outgassing and tidal fragmentation. The debate didn't resolve the mystery, but it did expose a critical fact: we do not have enough data to rule anything out definitively. This matters because it cracked open a door that had been nailed shut. Speculation about artificial objects in space was previously relegated to science fiction and conspiracy websites. Now, it appears in journals like the Astrophysical Journal letters. The methodology is careful. The language is hedged. But the ideas are there in print, with institutional affiliations attached. Why do mainstream journals publish speculative frameworks? Because the scientific method requires considering all possibilities that fit the data. If you cannot explain something with known processes, you are obligated to consider unknown ones. That includes intelligence. Excluding it a priori is bias, but including it requires extraordinary care because the history of false positives in this field is long and embarrassing. Consider the Drake equation. Frank Drake developed it in 1961 as a framework for discussion, not a calculation with real numbers. But people treat it like a formula that produces answers. They plug in optimistic values and conclude the galaxy must be teeming with life. They plug in pessimistic values and conclude we are alone. The equation doesn't tell you which is true. It tells you what factors matter. And one of those factors is L, the length of time technological civilizations remain detectable. If civilizations only broadcast for a few centuries before going quiet, either through extinction or intentional silence, then the detection window is incredibly narrow. We might be surrounded by civilizations that existed millions of years ago or will exist millions of years from now. But temporal overlap is rare. This is one solution to the Fermi paradox. We aren't detecting anyone because timing matters as much as distance. The problem is that speculation spreads faster than corrections. A paper proposing an unconventional explanation gets picked up by news outlets and presented without caveats. The headline reads, "Harvard professor says alien probe visited Earth." The paper actually says, "We cannot exclude the possibility that objects of artificial origin could be detected through anomalous acceleration." Those are not the same statement, but the correction never gets the same reach as the initial claim. Media amplification exists in tension with scientific caution. Journalists need stories that engage readers. Scientists need accuracy that withstands peer review. The incentives do not align. This creates a feedback loop where researchers become more reluctant to speculate publicly, which makes the few who do speculate look like outliers, which in turn makes their speculation seem more extreme than it is. Speculation thrives in informational gaps. When you do not have high-resolution images, when you cannot land a probe, when the object is millions of miles away and moving fast. Every measurement is incomplete. Incomplete data means multiple interpretations fit. And when multiple interpretations fit, people gravitate toward the most interesting one, not the most likely one. There is no evidence of artificial origin for 3I Atlas. That needs to be stated plainly. The observations we have are consistent with a natural comet, but consistency with natural processes does not equal proof of natural origin. It just means we cannot tell the difference yet. And that ambiguity is where speculation lives. There is also no precedent for certainty. We have never encountered something like this before. We do not have a control group. We do not have comparison cases. We are trying to figure out what is normal for interstellar objects when we have only confirmed 3 of them. That is not enough data to build reliable models. Baselines require repetition. You need to observe multiple instances of a phenomenon under different conditions before you can say what is typical. Oumuamua was elongated and accelerating. 2I Borisov looked like a regular comet. 3I Atlas falls somewhere in between. The variance is high enough that we cannot define normal yet. Framing speculation as a thought experiment is useful. It lets us ask, what if, without claiming what is? What if an object like this were artificial? What would we expect to see? How would it differ from natural phenomena? What tests could we run? These questions aren't endorsements of alien probes. They are exercises in preparedness. Because if something genuinely artificial ever does show up, we need to have thought through how we would recognize it. The challenge is that artificial objects might intentionally mimic natural ones. If you are crossing interstellar space and you want to avoid detection, you would design your craft to look like a comet or asteroid. You would use materials and trajectories that blend in. You would minimize energy emissions. You would coast on momentum whenever possible. This means the very signatures we would look for to identify artificial objects might be deliberately absent. So, if the object isn't hostile, if it's not a probe, if it's not sending greetings, then why would it come at all? That question pulls us into the second tier of terror. Maybe it didn't come for us. Maybe it came from something. Maybe it is running. And if something advanced enough to cross interstellar space is fleeing, what could possibly scare them enough to run? The answer may lie in the sheer violence of the cosmos itself. Astrophysical dangers are not hypothetical. They are inevitable. Gamma-ray bursts are the most lethal phenomena in the observable universe. When a massive star collapses into a black hole, it can release more energy in 10 seconds than our sun will emit in its entire lifetime. If that focused beam is pointed at a planetary system, it strips away the atmosphere and bathes the surface in radiation that sterilizes everything. There is no defense. You either weren't in the way, or you are dead. The terrifying aspect of a gamma-ray burst is the lack of warning. Light travels at the same speed as the destruction. By the time you detect the burst, you are already being hit. There is no time to evacuate. However, if a civilization possessed sophisticated enough sensors, they might detect the precursor signs, the gravitational waves arriving seconds earlier, or the specific neutrino flux of a star beginning its final collapse. That could give them hours or days, just enough time to run. Stellar flares from red dwarf stars can achieve similar devastation on a longer timescale. Many potentially habitable exoplanets orbit red dwarfs simply because they are the most common type of star in the galaxy. But red dwarfs are volatile. They produce superflares that can erode planetary atmospheres over millions of years. A civilization on such a world might have centuries to prepare. But eventually, they would need to leave. Then there are rogue black holes. These are more speculative, but no less terrifying. Because black holes do not emit light. You do not see them coming until they interact with something. If one passed through a solar system, it would gravitationally disrupt planetary orbits, potentially flinging worlds into the freezing void of interstellar space or sending them crashing into their parent star. An advanced civilization might detect the gravitational anomaly decades in advance, just enough time to evacuate. But here is what keeps cosmologists awake: the threats we haven't imagined yet. Phenomena that do not exist in our current models of physics. Dangers that emerge at scales or in conditions we have never observed. The universe is under no obligation to limit its catastrophes to things we have theorized about. There could be stellar processes, galactic events, or cosmological transitions that make gamma-ray bursts look manageable by comparison. Why would refugees flee silently? Because noise attracts attention. If you are running from something, the last thing you want to do is announce your position to whatever is chasing you. You minimize your electromagnetic signature. You coast on momentum rather than using energy-intensive propulsion that flares like a beacon. You blend in with natural objects as much as possible. A comet is perfect camouflage. Trajectory implications matter here, though claiming intent requires more data than we currently possess. If 3I Atlas were truly fleeing something, its velocity vector should point away from a specific region of space. Astronomers can trace its path backward, calculating roughly where it came from. So far, those calculations show it originated from somewhere in the general direction of the constellation Cassiopeia. That tells us almost nothing. Cassiopeia covers a huge swath of sky containing millions of stars. But if the trajectory were refined and pointed to a specific stellar system, the implications would shift. Imagine receiving confirmation that 3I Atlas originated from a star system we have studied, one where we detected exoplanets in the habitable zone, one that seems stable and unremarkable. And now, something from that system is racing away at interstellar velocities, taking a trajectory that happened to bring it past Earth. Is it coincidence, or a calculated path that takes it as far from its origin point as physics allows? The psychological impact of a refugee scenario is the fear of an unseen third party. You are not scared of the visitor. You are scared of what made the visitor run. It is the same primal fear you feel when someone sprints past you in a panic, looking over their shoulder. Your instinct is to run, too, but you don't know which direction is safe. This leads to predator-prey cosmology, a framework that reframes the Fermi paradox. Instead of asking why we haven't found anyone, it asks why we haven't been found. The answer could be that successful civilizations learn to hide. They stop broadcasting. They minimize their presence. They go dark. And the ones that do not go dark disappear. The horror here is asymmetry. In a predator-prey cosmos, you do not know if you are predator, prey, or irrelevant. You do not know if being loud is dangerous because you will attract predators, or if being quiet is dangerous because you won't attract allies. Every choice is a gamble made with incomplete information. And there is another layer. If 3I Atlas is a refugee, it means someone survived long enough to evacuate, long enough to build interstellar capability, long enough to recognize the danger and respond. But where did they go? If they are running, do they have a destination, or are they just putting distance between themselves and the threat? Hoping that space itself provides safety, the object we are observing might not be a ship. It might be a lifeboat, the remnant of something larger that didn't make it. But there is a level beyond distress, a message that doesn't just imply danger, but specifies it, not through description, but through instruction: stop broadcasting. And the reason becomes clear when you understand what is listening. Let's return to the hard science of 3I Atlas. Comets are often described as dirty snowballs. That is the simplest description, a mixture of water ice, frozen gases like carbon dioxide and methane, and dust particles made of silicates and organic compounds. When a comet approaches the sun, the ice sublimates directly from solid to gas, creating the coma atmosphere and tail we associate with these objects. This process is well understood for comets that formed in our own solar system. Interstellar chemistry, however, is expected to be weird. A comet that formed around a different star experienced different temperatures, different radiation environments, and different elemental abundances. The proportions of various ices depend on where the comet condensed in its birth system. A comet from a carbon-rich system might have more organic compounds. One from a system with a massive gas giant might have been gravitationally perturbed before it fully formed, giving it an unusual internal structure. The carbon dioxide to water ratio in 3I Atlas is within known ranges. But on the high end, most solar system comets show water as the dominant volatile. 3I Atlas shows carbon dioxide as more prominent in certain outgassing episodes. This isn't unprecedented. Comet 29P Schwarzmann-Wachmann 1 exhibits similar behavior, but it is uncommon enough that it gets flagged in observational reports. What makes this interesting is consistency. When you observe the same anomaly across multiple observation windows, using different instruments from different locations, it starts looking less like instrumental error and more like a real feature. The CO2 dominance in 3I Atlas persists. It is reproducible, which means it is telling us something about either the object's formation environment or its current behavior. Jet behavior adds another layer of complexity. When comets outgas, they don't do it uniformly. Localized vents on the surface produce jets that can change the object's rotation and create asymmetric forces, tiny pushes that alter its path. These non-gravitational accelerations are normal, but predicting them accurately requires knowing the surface structure in detail, which we do not have for 3I Atlas. So, when the object accelerates slightly in ways that do not match initial models, it is not necessarily shocking. It is expected uncertainty. But here is where it gets complicated. The jets from 3I Atlas do not follow the pattern you would expect from a simple rotating body with random surface features. They seem to activate at specific points in the orbit. Not random points, specific ones. This could be because certain areas of the surface only heat up enough to outgas when they reach particular distances from the sun. Perfectly natural. But it could also mean the surface has a structure we are not accounting for. Possibly natural structure. Possibly not. Anomalies do not equal artificial. This point cannot be stressed enough. Finding something unusual does not mean you found something engineered. It means you found something you need to study more. The universe is full of natural phenomena that violate our assumptions because our assumptions were incomplete. Tabby's star, officially KIC 846285, is the classic example. For years, it showed bizarre dimming patterns that did not match any known astrophysical process. Speculation ran wild alien megastructures, Dyson swarms, advanced civilizations harvesting stellar energy. Then, more observations came in, and the likely explanation emerged: a massive, uneven debris field, probably from a shattered comet or planetesimal, creating irregular eclipses. It was natural. It was disappointing to some, but it was ultimately explicable. However, anomalies do equal narrative instability. When you cannot give a definitive explanation, people fill in their own, and the longer anomalies persist across multiple objects, the more they start to feel like a pattern rather than noise. Oumuamua had anomalies. 2I Borisov had fewer, which reassured people. Now 3I Atlas has its own set. You start wondering if interstellar objects are just intrinsically weird, or if we are missing something systematic. Observer bias matters. 2. If you expect something to be strange, you pay closer attention to the strange parts and downplay the normal parts. This is why peer review exists, to catch the moments when a researcher becomes too invested in an anomaly to evaluate it dispassionately. But peer review also means that anomalies which survive scrutiny have to be taken seriously. We must also acknowledge instrumentation limits. We are observing 3I Atlas from tens of millions of miles away. The best telescopes on Earth can barely resolve it as more than a point of light. Space-based telescopes have better resolution but limited observation windows. We are reconstructing its properties from indirect measurements, like trying to identify an animal by studying its shadow. Spectroscopy gives you chemistry, but not structure. You know what elements are present, but you don't know how they are arranged. Photometry gives you brightness changes, but not causation. You know it is getting brighter or dimmer, but you don't know exactly why. Astrometry gives you position, but not intent. You know where it is going. You do not know if that is deliberate. This ambiguity places the object squarely in the realm of the unknown. And edge cases in astrophysics are where new physics gets discovered. Pulsars were an edge case. Black holes were an edge case until we detected them directly. Fast radio bursts, FRBs, are still an edge case we are trying to understand. Dismissing these anomalies too quickly means missing opportunities. Obsessing over them too much means wasting resources on statistical flukes. The universe does not owe us clarity. That is the uncomfortable truth. Objects can be ambiguous. Data can be incomplete. Phenomena can exist that we simply do not have the tools to explain yet. Being comfortable with that uncertainty is part of doing science honestly. But it doesn't make the uncertainty less unnerving. Because uncertainty creates space for imagination. And human imagination, when faced with cosmic mysteries, rarely settles on boring explanations. The Fermi paradox is older than most people realize. Physicist Enrico Fermi posed the question in 1950 while discussing the probability of extraterrestrial civilizations with colleagues. The logic is brutal. If intelligent life is common, and if even a few civilizations develop interstellar travel, then where are they? Why haven't we seen evidence of galactic colonization? The galaxy is billions of years old. Even slow expansion at sublight speeds should have filled it by now. Dozens of solutions exist. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations destroy themselves before they expand. Maybe they are out there. But we are not looking in the right way. Each solution has proponents and problems. None are definitive. The Great Silence is the observational manifestation of this paradox. We have been listening for decades, SETI programs have scanned thousands of stars. We found nothing. No radio signals. No laser pulses. No megastructures blocking starlight. The universe appears empty of technological civilizations, at least. Empty of ones that broadcast. But what if the silence isn't absence? What if it is strategy? That is where the dark forest theory enters the conversation. The name comes from a science fiction novel by Liu Cixin. But the concept predates the book. It is based on game theory applied to cosmic scales. The universe is a dark forest. Every civilization is an armed hunter moving silently through the trees like a ghost. You do not know if other hunters are friendly or hostile. You do not know their capabilities or intentions. So, you stay quiet. You listen. And if you detect someone else, another hunter snapping a twig, breathing too loud, you face a terrible choice. Do you risk contact? Do you reveal yourself and hope they are friendly? Or do you eliminate the potential threat before it can eliminate you? Because once you know they exist, they might know you exist too. And the first civilization to strike has an enormous advantage. This creates a cosmic Mexican standoff. A tense deadlock where every civilization remains hidden because revealing one's location could be fatal. While this is a theoretical risk model rather than a proven fact, it is grounded in a thought experiment regarding how rational civilizations might behave based on 4 grim assumptions: that cosmic resources are scarce, that civilizations will inevitably expand and compete. That distance makes it impossible to ever fully trust another species' intentions, a concept known as the chain of suspicion. And finally, that the physics of the universe makes destroying a civilization far easier than defending one. Given these assumptions, the rational strategy is silence and preemptive strikes against anyone who breaks it. Whether these assumptions hold for non-human intelligence is unknown. Maybe alien civilizations are inherently cooperative. Maybe they have solved scarcity. Maybe their psychology doesn't include paranoia. Or maybe it does, and they have learned through bitter experience that loudness equals death. Silence could also be strategic in ways that have nothing to do with deliberate hiding. Maybe advanced civilizations simply stop using technologies that leak electromagnetic radiation. They switch to more efficient communication methods that do not broadcast waste energy into space. Quantum communication, for example, is point-to-point with no interception possible. Contained networks do not emit stray signals. As technology improves, the signature shrinks. Eventually, a civilization becomes invisible, not because they are trying to hide, but because their technology is so refined it produces no waste. This creates a selection bias in what we detect broadcast versus listen. If most civilizations eventually go quiet either through extinction or technological maturation, then the ones we are most likely to detect are either very young or very reckless. Young civilizations haven't learned the danger yet. Reckless ones don't care. Both are temporary states. You either mature and go quiet, or you get eliminated by something that noticed your noise. This period is known as technological adolescence. It is the time when a civilization is loud but vulnerable. You have radio. You have nuclear weapons. You have satellites. But you do not have interstellar travel. And you do not have planetary defense against external threats. You are shouting into the galaxy without knowing who is listening. And you are too primitive to protect yourself if the wrong entity hears you. Earth has been in technological adolescence for about a century. That is nothing on cosmic timescales. But it is also the most dangerous period in our history. We are advanced enough to be noticeable, but not advanced enough to survive contact with something superior. We are a child wandering through a forest, calling out to see if anyone is there, unaware that predators exist. And Earth is unusually loud. We are not trying to hide. We light up the night side of our planet with so much artificial light that it is visible from space. We fill the radio spectrum with communication signals. We have detonated thousands of nuclear weapons, each one releasing isotopes detectable across interstellar distances. We have been drawing attention to ourselves for decades. The Arecibo message in 1974 was a deliberate broadcast, a coded message sent toward the globular cluster M13, 25,000 light-years away. It contained information about humanity, our DNA, our solar system, even a crude image of a human. The message won't arrive for millennia, but it is out there, permanent, irrevocably. Framing silence as evolved behavior suggests that the civilizations we don't detect aren't absent. They are careful. They learned something we haven't learned yet. They figured out that survival requires restraint, and if that is true, then the question becomes, what taught them? Was it a close call, or was it something worse? And if silence equals survival, then maybe that is the only message worth sending across interstellar distances. Not greetings, not math, just a warning: be quiet. Stop broadcasting before something hears you. The arrival of 3I Atlas has not just stirred the scientific community, it has ignited the public. Reddit threads about the object run hundreds of comments deep. Amateur astronomers post their own observations, comparing notes on brightness fluctuations and trajectory calculations. Some of this is solid work. People with backyard telescopes and CCD cameras can contribute meaningful data when enough of them coordinate. But the signal-to-noise ratio is terrible. Misinterpretation of brightness changes is common. Comets rotate. As they rotate, different parts of their surface reflect sunlight at different angles. This creates variability in brightness that is perfectly predictable if you know the rotation period and surface features. But if you don't know those things, the variations look random, and random variations trigger pattern-seeking behavior. People start seeing pulses where none exist. Someone posts a light curve showing regular dips. Another person points out those dips correspond to Earth day intervals. Speculation erupts. Is it signaling? Is it time to our rotation? The more prosaic explanation that the observer was taking measurements at the same time each night. Introducing observational bias gets lost in the noise. The exciting explanation spreads. The boring truth doesn't. Observational artifacts are another issue. Atmospheric turbulence affects ground-based observations. Satellite trails cross the field of view. Cosmic rays hit camera sensors and create false signals, hot pixels. Every amateur astronomer learns to filter these out. But it takes experience. Newcomers capture anomalies that aren't real and share them online, where they get amplified by people who don't know the difference. Velocity misunderstandings generate their share of confusion. Interstellar objects move fast relative to the sun, but that doesn't mean they are accelerating. Their speed is constant in the absence of forces acting on them. When people see that 3I Atlas is moving at tens of kilometers per second, they assume propulsion. But gravitational slingshots around massive objects can achieve those speeds naturally. Jupiter alone can boost an object's velocity by dozens of kilometers per second if the trajectory is right. Misinformation propagates through social networks faster than facts. A misleading claim gets shared thousands of times before anyone fact-checks it. By the time a correction is posted, the original claim has reached people who will never see the rebuttal. This isn't unique to astronomy. It is a structural problem with how information spreads online. Novelty gets amplified. Correction gets ignored. But distrust of institutions exists for real reasons. Scientists sometimes communicate poorly, using jargon that alienates non-specialists. Press releases get written by public relations departments that prioritize engagement over accuracy. Governments have histories of classifying information about aerial phenomena, creating suspicion about what else might be hidden. All of this erodes trust. The Pentagon's UAP unidentified aerial phenomena reports added fuel to this fire. For decades, the government dismissed UFO sightings as misidentifications, hoaxes, or delusions. Then, in 2021, official reports acknowledged that some aerial phenomena remain unexplained. This validated people who had been claiming cover-ups for years. The UAP report of 2021 didn't prove aliens, but it proved that decades of dismissals had been premature. Trust, once broken, is hard to rebuild. Transparency challenges in this field are genuine. Some observations are classified because they come from military sensors designed to track ballistic missiles, not asteroids. Some data isn't published immediately because researchers want to verify it before releasing findings that could ruin their careers if wrong. These delays are professionally responsible, but they create informational voids that get filled with speculation. Nature abhors a vacuum. So does the internet. Secrecy accusations emerge whenever information is incomplete. If scientists can't explain something fully, people assume they are holding back. If governments delay releasing data, people assume it is proof of something extraordinary. The absence of information gets interpreted as confirmation rather than uncertainty. This is a cognitive error, but it is a predictable one. Public fear is often rational uncertainty. People know they do not have access to all the data. They know that major discoveries take time to verify and announce. They know that by the time information reaches them, it has been filtered through multiple layers of bureaucracy and media interpretation. So, when something unusual appears in the sky and the official explanation sounds incomplete, skepticism isn't irrational. It is reasonable doubt. The problem is when reasonable doubt metastasizes into unreasonable certainty. When we don't know yet becomes they are lying to us, which becomes it is definitely aliens and they are covering it up. That progression happens fast online because confirmation bias is powerful. People seek out information that supports what they already believe and ignore information that contradicts it. Even false signals reveal true anxieties. When someone interprets a natural phenomenon as artificial, they are expressing a belief that contact is possible and imminent. When someone distrusts official explanations, they are expressing a belief that they are not being told the full truth. These beliefs might be wrong in specific cases, but they are not absurd in general. Contact is possible. Institutions do withhold information. The question is whether 3I Atlas is an example of this dynamic. And there is a deeper anxiety underneath all of this, the fear that we are not prepared. That if something significant happens, whether it is first contact or a genuine threat, the institutions we rely on won't handle it well. That we will find out too late. That decisions will be made in closed rooms without public input. That by the time ordinary people learn what is happening, it will already be over. This fear isn't entirely unjustified. History provides plenty of examples of institutional failure, which leads to the question that bridges all three levels of terror. Are we looking at a warning, not a greeting? Not a threat, but an urgent message that we have already missed the point. Because warnings only work if you recognize them as warnings. And if you are busy debating whether something is natural or artificial, you might miss the fact that it is neither. It is educational. It is trying to teach you something you need to know before it is too late. Let's summarize where we are. We have established that 3I Atlas is observable, that it exhibits behaviors largely consistent with natural phenomena, but that anomalies exist within error margins. We have explored how messages could arrive not as deliberate transmissions, but as observable patterns. We have examined the confusion level, where mirroring proves surveillance. We have walked through the distress level, where the visitor is a refugee fleeing something worse. And now we are approaching the edge of the third level, where the message isn't about the sender at all. It is about us. The hypothesis goes like this. What if certain behaviors we observe aren't meant to convey information about the object's origin or composition? What if they are meant to convey instructions, not complex instructions? Not detailed star maps or mathematical proofs. Just a simple directive encoded in the simplest possible way. A warning. Evolutionary survival messaging would be minimal by necessity. If you are trying to communicate with a species you know nothing about, you cannot use language. You cannot assume shared cultural references. You cannot even assume they process information the same way you do. So, you would use the most basic form of communication, deviation from expected patterns. You do something that looks wrong according to natural laws, something that can only be interpreted as deliberate. Think about what that means in practice. A comet that outgasses at intervals that correlate with prime numbers. A trajectory that adjusts in ways requiring forces we cannot account for. Chemical signatures that oscillate between states faster than thermodynamics should allow. Nothing elaborate. Nothing that screams artificial intelligence sent this, just enough wrongness that scientists cannot dismiss it, cannot explain it away, and cannot stop thinking about it. The message is in the impossibility itself. The challenge with minimal messaging is ambiguity. The simpler your message, the more interpretations it allows. If you just flash a light 3 times, does that mean danger, hello, look here, or something else entirely? Context matters. But context is exactly what you do not have when communicating across species that evolved independently. So, minimal messages have to rely on universal concepts, mathematics, physics, things that should be constant regardless of biology or culture. But even universal concepts can be misunderstood. The Arecibo message, sent in 1974, used binary code to represent numbers, chemical formulas, and crude images. We assumed any technological civilization would understand binary. We assumed they would recognize DNA structure. We assumed they would interpret the patterns the way we intended. But what if they don't? What if their mathematics develop differently? What if they see our message and interpret it as noise or worse, as a threat display? Why would warnings be minimal? Because elaborate messages require shared context. They require that both sides understand the code, the syntax, the semantic framework. But a warning only needs to say stop, change course, don't do that. The content of the warning is less important than the fact that a warning was issued. If you see someone waving their arms frantically at you while you are walking toward a cliff, you stop. You do not need to understand their language to know something is wrong. The urgency transcends translation. The same principle applies at cosmic scales. If you want to warn a civilization about danger, you do not need to explain the nature of the danger in detail. You just need to convey urgency and direction. Stop broadcasting. Be quiet. Hide. The specifics of why can come later if there is time. The immediate goal is behavior change. Get them to stop doing the thing that is putting them at risk. Ambiguity could even be intentional. If you want to warn someone without revealing too much about yourself, you make the warning unclear enough that it cannot be traced back definitively. You give them enough information to change behavior, but not enough to locate you. This is especially important if the danger is detection itself. If being found is the risk, then your warning cannot make you findable. You have to balance urgency with anonymity. This creates a paradox. The more specific your warning, the more useful it is. But the more it reveals about you, the more you explain about the danger, the more you expose about what you know and how you know it. So, You stay vague. You hint. You create just enough disturbance in the data that someone paying attention will notice something is wrong. But not so much disturbance that predators notice you are the one doing the warning. The cost of misinterpretation is extinction level. If a civilization misreads a warning as a greeting, they might respond in ways that escalate danger. They might broadcast back. They might send detailed information about their location, their capabilities, their resources, all the things a predator would want to know. If they misread silence as absence, they might continue behaviors that attracted attention in the first place. Keep broadcasting. Keep being loud. Keep making themselves targets. The margin for error is zero. You cannot afford to get this wrong. History is full of misinterpreted warnings on smaller scales. Animals that display warning coloration to signal poison sometimes get eaten anyway by predators that do not recognize the pattern. Fire alarms that sound too often get ignored when there is a real fire. The boy who cried wolf loses credibility until the wolf actually comes. Warnings only work if they are received correctly, interpreted correctly, and acted upon correctly. Any failure in that chain means the warning was worthless. What would we warn about if we discovered a young civilization? Think about it. If Earth's astronomers detected technosignatures from an exoplanet and we knew something about the galaxy that they didn't, what would we try to communicate? We would tell them to be careful. We would tell them that broadcasting has consequences. We would tell them that the universe is more dangerous than they think. Not because we are hostile, but because something else is. We would want them to know that their radio signals are traveling outward at the speed of light, announcing their presence to anyone within range. We would want them to know that visibility equals vulnerability. We would want them to understand that the great silence might not be absence, but strategy, that the civilizations that survive are the ones that learn to hide. And we would want them to learn this lesson before it is too late, before they attract the wrong kind of attention. This raises an interesting philosophical question. Do you have an obligation to warn others of danger, even if warning them might draw attention to you? If you have survived by being quiet and you encounter someone being loud, do you risk your own safety to tell them to shut up, or do you stay hidden and hope they figure it out on their own? Different ethical frameworks would answer differently. Utilitarian ethics might argue, yes, warn them. The benefit of saving an entire civilization outweighs the risk to yourself. Deontological ethics might argue you have a duty to prevent harm whenever you can. But survival ethics, the kind of morality that evolves when existential threats are real and constant, might simply say no. Do not risk yourself for strangers. Your survival is paramount. Let them learn the hard way, just as you did. The galaxy is full of hard lessons, and it is not your responsibility to teach them all. This brings us to the concept of irreversible knowledge. Once you learn something, you cannot unlearn it. Once you realize that silence might be survival, you cannot go back to assuming the universe is empty. The warning changes you. Even if you do not fully understand it, you become cautious in ways you weren't before. Your behavior shifts. You start questioning assumptions you had never questioned. You second-guess decisions that once seemed obvious. This is the power of doubt. Before the warning, you operated with certainty. You believed the universe was empty, or at least uninhabited by anything dangerous. You could broadcast freely. You could explore openly. You could assume that first contact, if it happened, would be benign or at least neutral. After the warning, all of that disappears. You don't know what is out there. You don't know if you are safe. Every transmission becomes a risk calculation. Every signal you send might be the one that gets you noticed. So, imagine this scenario. 3I Atlas arrives. It does nothing overtly threatening. It follows a trajectory that brings it close to Earth at a specific time. It exhibits chemical and physical properties that are almost but not quite explicable. It creates just enough doubt that astronomers keep analyzing, keep debating, keep publishing papers, and in doing so, it gets humanity's attention. Getting attention might be the entire point, not to announce themselves, but to make us think, to make us question whether we are alone, to introduce doubt where certainty existed before, because once you doubt you are alone, you start behaving differently. You become more aware, more cautious. You start thinking about what messages you are sending. You start wondering who might be listening. The beauty of this approach is that it requires no complex technology, no radio transmission, no laser communication, no mathematical proofs encoded in trajectories. Just an object that is weird enough to make scientists uncomfortable. Weird enough to generate papers and conferences and public interest. Weird enough that humanity collectively starts asking questions it wasn't asking before. And those questions change us. They change our relationship with the cosmos. We stop assuming we are alone. We stop assuming we are safe. We start considering possibilities we once dismissed as science fiction. What if someone is watching? What if broadcasting is dangerous? What if we need to be more careful about what signals we send into space? The warning works not through explicit instruction, but through implication, through making us aware of possibilities we had ignored. The scariest message wouldn't ask anything of us except silence. It wouldn't demand submission or tribute. It wouldn't threaten invasion. It would just say, "You have been noticed. Stop making noise." Because there is something out there that listens for noise, and you do not want to meet it. That is the dark forest level, and it is worse than war. Because war has rules, war has objectives, war has victory conditions and defeat conditions. War ends. One side wins. The other loses. Terms are negotiated. Treaties are signed. Life continues in some form, but hiding from an invisible predator is a permanent condition. You never know if you are safe. You never know if the danger is past or if it is still out there waiting. Watching, listening. You never know if being quiet is enough, or if being noticed once means you are marked forever. Maybe the predators catalog every loud civilization they detect, prioritizing targets based on technological level and resource value. Maybe they wait until you are more developed before harvesting. Maybe they are patient on timescales that make centuries seem like seconds. The uncertainty becomes a prison. You are trapped not by walls, but by fear of what might be outside those walls. And the worst part is, you built the prison yourself by being loud in the first place. Every radio broadcast, every television signal, every radar pulse for the past 100 years has been expanding outward at the speed of light. You can't take them back. You can't recall them. They are out there, announcing Earth's presence to anyone within listening range. The only question is whether anyone is listening, and what they will do if they hear you. This is the existential weight of the warning. It tells you that the rules have changed, that assumptions you based your entire civilization on might be wrong, that the universe isn't the benign, empty place you hoped it was, that there are consequences for actions you took in ignorance. And those consequences might be coming. They might already be on their way. And there is nothing you can do except go quiet and hope that is enough. Hope you are not already too late. Here is the message in its simplest form: stop broadcasting. Not, we come in peace. Not prepare for contact. Not surrender or D. Just two words encoded in whatever minimal way is necessary to convey urgency without complexity. Maybe it is a repeating pattern in outgassing that cannot occur naturally. Maybe it is a trajectory adjustment timed to coincide with Earth's position that requires intelligence to execute. Maybe it is something we haven't noticed yet because we are not looking for instructions, we are looking for information. Why is this worse than a declaration of war? Because war gives you something to fight. War tells you who the enemy is, what they want, and how they plan to take it. You can prepare, you can strategize, you can mobilize. You can die knowing why. But this message doesn't give you an enemy. It gives you a constraint: stop broadcasting. And the reason isn't explained because explaining would itself be broadcasting. The message is recursive. Its meaning depends on obeying it immediately. The implication of predators is unavoidable. If someone is warning you to be quiet, it means noise is dangerous. And if noise is dangerous, something must be hunting the noisy. You don't know what it is. You don't know where it is. You don't know its capabilities or its motivations. You only know that someone who survived long enough to reach you thinks you are in danger. And their solution is silence. Noise-based detection is how we search for technosignatures. We look for electromagnetic emissions that do not match natural sources. We scan for laser pulses, radio signals, and artificial chemicals in exoplanet atmospheres. Narrowband radio signals are particularly suspicious because natural processes tend to produce broadband noise. A signal concentrated in a narrow frequency range suggests a transmitter. An oscillator, something designed. If we can detect civilizations this way, then so can others. This creates a fundamental asymmetry in the cosmos. Detection is passive. You can listen without revealing yourself. But broadcasting is active. Every signal you send is an announcement. Every transmission is a billboard saying, "Here we are," to anyone with the right equipment. The listener has all the advantages. The broadcaster has none. Connecting this to evolutionary silence creates a chilling framework. Civilizations that broadcast go extinct. Civilizations that don't broadcast survive. Over millions of years, natural selection favors the quiet ones. Not because quiet civilizations are inherently superior, but because loud ones get eliminated. The selection pressure is external. Something in the galaxy removes broadcasters. What remains is a universe full of civilizations that exist but do not announce themselves. Cosmic hunter logic is straightforward. If you are a predatory civilization harvesting resources, you do not waste energy searching randomly. You wait for prey to reveal themselves. You monitor the galaxy for anomalous signals. When someone broadcasts, you note their location. You assess their technological level. You determine whether they are worth exploiting. Young civilizations are easy targets. They do not have defenses. They do not expect attack. They are loud precisely because they are naive. This model assumes certain things about alien psychology. It assumes that resource competition exists. It assumes that some civilizations prioritize expansion and acquisition. It assumes that interstellar travel is possible, but costly enough that you would target your efforts rather than roaming blindly. These assumptions might be wrong, but if they are even partially right for even one predatory civilization, then everyone else needs to hide. One wolf in the forest means all the deer stay quiet. Earth's century of broadcasts is our vulnerability. Radio and television signals have been leaking into space since the 1920s. We have sent deliberate messages via SETI projects, like the Arecibo transmission in 1974. Those signals are out there. They cannot be recalled. They are expanding outward at the speed of light, creating an ever-growing sphere of revelation. Anyone within a 1 to 100 light-year radius knows we are here. Anyone within 50 years of travel time could reach us within a human lifetime, assuming they have the technology and motivation. The Voyager Golden Records are another example. Launched in 1977, both Voyager probes carry gold-plated records containing sounds and images from Earth. They include greetings in 55 languages, music from different cultures, and even encoded images showing human anatomy and Earth's location in the galaxy. The intention was to create a message for any extraterrestrial intelligence that might find them. But the probes also reveal where we are. They are traveling slowly, so they won't reach another star system for tens of thousands of years. But if someone intercepts them, they have a map back to us. Irreversibility is the core of the horror. You cannot take back what you have already transmitted. The damage is done. If the dark forest hypothesis is correct, we have already painted a target on ourselves. The only variable left is time. Did anyone notice? And if they did, how long will it take them to respond? Decades, centuries, millennia. This uncertainty condemns a civilization to live in perpetual anxiety. Every year that passes without incident forces you to wonder, are we safe? Or is the response just slow? You never get resolution. Fear without a villain is more psychologically corrosive than fear with one. When you have an enemy, you can hate them. You can blame them. You can focus your fear into anger and action. You can build defenses, make plans, rally allies. But when the threat is structural, when it is simply the way the universe works, there is nothing to fight. You can only accept the new rules and live under them. You cannot punch the darkness. You can only hide from it. Let the silence linger. That is what a warning would do. It wouldn't elaborate. It wouldn't explain. It would just stop, leaving you to figure out what it means and whether you are going to listen. Because the warning only works if you change your behavior. And changing your behavior means accepting that everything you thought about humanity's place in the universe was wrong. We thought we were explorers, pioneers, the first to look up and wonder. But what if we are just the latest in a long line of civilizations that made the same mistake? What if the galaxy is full of ruins belonging to species that were too loud? What if silence isn't the absence of civilization, but the presence of civilizations wise enough to hide? And what if we are running out of time to join them? This leads us to a critical realization in modern astrophysics. Techno-signatures might have an expiration date. This concept is reshaping SETI's strategy. If civilizations follow certain technological trajectories, they might only be detectable for a brief period, perhaps a few hundred years, maybe 1,000. After that, they transition to technologies that do not emit detectable signals. Think about Earth's radio emissions. We have been broadcasting for about a century, but those broadcasts are already declining in strength. Modern communication uses fiber optic cables instead of radio waves. Satellite transmissions are tightly beamed toward the ground, rather than being omnidirectional broadcasts into space. Digital compression makes signals more efficient, which means less wasted energy radiated into the cosmos. We are getting quieter, not because we are trying to hide, but because quiet is more efficient. In another century, Earth might be significantly quieter than it is now. Even as our civilization continues advancing, we will still be here. Still technological, still communicating. But our communication will be contained, point to point, and encrypted. Someone looking at Earth from 100 light-years away might see a planet with oxygen in its atmosphere, but no radio signals. They would have no way to know we are technological unless they got close enough to see our cities, our satellites, or the chemical byproducts of our industry in the atmosphere. AI-driven civilization transitions could accelerate this process. Once artificial intelligence surpasses human-level cognition, communication might shift to forms we cannot intercept or even understand. Neural interfaces could replace electromagnetic transmission entirely. Data transfer could happen through quantum entanglement, which does not propagate through space in detectable ways. Computation could become so efficient that waste heat drops below ambient temperature variations, making it invisible to infrared telescopes. An AI civilization might be vastly more advanced than ours, yet completely invisible to current search methods. This creates a sampling problem. If technosignatures only last a few centuries per civilization, and civilizations are spread across billions of years of galactic history, the odds of two civilizations being detectable at the same time are vanishingly low. It is like trying to see two fireflies flash simultaneously in a vast field at night. They are both there. They are both flashing. But their light only lasts a moment. And the chances of those moments overlapping from your perspective are slim. We might be searching for signals that existed a million years ago or won't exist for another million years. Synchronization matters. The galaxy could be full of civilizations, but if they are all in different phases of technological development, we would never detect each other. We would be ships passing in the night, each one flashing its lights at times when no one else is looking. The idea of post-observable intelligence is unsettling. It suggests that the most advanced civilizations are the ones we cannot see, not because they are hiding necessarily, but because their technology is so refined it produces no detectable byproducts. They have transcended the messy, noisy phase of technological development. From our perspective, they are indistinguishable from empty space. They could be everywhere. They could be watching us. We would never know. This inverts our assumptions about the search. We have been assuming that advanced civilizations would be loud, that they would build Dyson spheres and megastructures, that they would terraform planets and light up the galaxy with their industry. But what if advancement means the opposite? What if maturity means minimalism? What if the most successful civilizations are the ones that learn to do more with less, to operate so efficiently that they leave no trace? Connecting silence to efficiency makes evolutionary sense. Natural selection applies to technologies. 2. Systems that waste energy lose out to systems that don't. Communication methods that reveal your position to potential threats lose out to methods that don't. Over time, civilizations converge on quiet efficiency, not because they are afraid, but because it is optimal. Loudness is waste. Waste is disadvantage. Disadvantage leads to failure. Why loud civilizations might not last is a different question with darker implications. Maybe inefficient broadcasting correlates with other vulnerabilities. Maybe civilizations that haven't learned to minimize their signature also haven't learned to manage other existential risks: climate instability, nuclear proliferation, engineered pandemics, unaligned artificial intelligence. Loudness might be a symptom of immaturity, and immature civilizations tend to self-destruct before they learn restraint. Survivorship bias applies to the civilizations we might detect. If only young or reckless civilizations broadcast, then SETI is selecting for exactly the kinds of civilizations that do not last. We are searching for the doomed ones. The survivors are invisible, and if we do detect someone, it might mean they are about to disappear. They are in the window, the brief, dangerous window between the discovery of radio and the discovery that radio was a mistake. Framing Earth as immature isn't about self-deprecation. It is about recognizing where we are in the developmental timeline. We are a single-planet species with primitive propulsion technology and no planetary defense against external threats. We can barely detect asteroids in our own solar system with enough warning to do anything about them. We have no way to defend against intentional attack from a more advanced civilization. We are vulnerable because we are new at this. And we are loud. We are broadcasting our presence without understanding the consequences. We are the teenagers of the galaxy, playing music too loud at a party, unaware that the neighbors have already called the police. Except the police might not be coming to shut down the party. They might be coming to eliminate the noise permanently. Reinforcing the danger of visibility connects back to the warning hypothesis. If advanced civilizations know that visibility correlates with extinction, they might warn newcomers who don't know yet. Not out of altruism, but out of pragmatism. Fewer loud civilizations means fewer opportunities for predators to hunt. A quieter galaxy is safer for everyone who has learned to be quiet. Warning, the loud ones benefits the quiet ones. It is enlightened self-interest. This ties directly back to the dark forest warning. If 3i Atlas carries any message, it might not be about the object itself. It might be about our behavior, about the fact that we are still broadcasting without understanding the stakes, about the need to stop before something notices, before the window closes, not because we matured, but because we were eliminated. The message isn't here we are. It is there you are, and that is dangerous. To understand what we might be missing, we must look at multi-messenger astronomy. This is the practice of observing cosmic events using multiple types of signals simultaneously: light, gravitational waves, neutrinos, and cosmic rays. Each type of signal carries different information. Light tells you about chemistry and temperature. Gravitational waves tell you about massive objects accelerating violently. Neutrinos pass through matter and reveal nuclear processes happening inside stars. Cosmic rays are high-energy particles that might point back to their sources if you can trace their trajectories through galactic magnetic fields. The reason this matters is that single-channel observation is incomplete. If you only look at visible light, you miss X-rays and gamma rays. If you only monitor radio waves, you miss gravitational waves. Each type of signal reveals different aspects of the same phenomenon. A neutron-star merger produces gravitational waves, gamma ray bursts, and eventually a kilonova that shines in visible light. Miss any one of those channels, and you miss part of the story. The 2017 detection of GW1708 17 was groundbreaking because it combined all these channels. LIGO detected the gravitational waves. Fermi and integral satellites detected gamma rays. Dozens of optical telescopes watched the afterglow. This single event confirmed that neutron-star mergers create heavy elements like gold and platinum. It validated decades of theoretical models, but it only worked because we were watching with everything we had. Fast radio bursts, FRBs, are a prime example of how easily signals hide in plain sight. These are millisecond duration pulses of radio emission arriving from cosmological distances. The first one was technically discovered in 2001, but it wasn't recognized as a new phenomenon until 2007. When an astronomer was reviewing archived data, we weren't looking for them because we didn't know they existed. Now, we know they are common, occurring thousands of times per day across the observable universe, but we still don't understand what causes most of them. Some repeat, some don't. Some come from galaxies with active star formation, others come from older, quieter galaxies. The diversity suggests multiple mechanisms, but we cannot observe the sources directly. We only see the bursts themselves. It is like trying to understand an animal by studying the sounds it makes without ever seeing the animal. You get clues, but you are missing the full picture. Transient events are another category of phenomena we routinely miss. Supernovae last weeks. Gamma ray bursts last seconds. Tidal disruption events, where a star gets torn apart by a black hole, can last months. But the initial brightening happens in days. If your telescope is pointing at the wrong part of the sky when one occurs, you do not get a second chance. This is why networks of automated telescopes scan the night continuously, flagging anything that changes. The Vera Rubin Observatory, when it comes online, will photograph the entire visible sky every few nights. That sounds comprehensive until you realize that events lasting hours or minutes will be missed between observations. You cannot watch everything constantly. You have to choose, and every choice is a gamble that you are not missing something crucial. Misclassification risks are real. Algorithms flag anomalies based on how much they deviate from training data. But if the training data doesn't include examples of a particular phenomenon, the algorithm might categorize it as instrumental error. Early pulsars were almost dismissed as interference. Someone literally wrote LGM for little green men on the printout as a joke. If the signal had been slightly less regular, or if the researcher had been less persistent, we might have dismissed it as noise. Fast radio bursts were initially thought to be glitches. The first few detections were ignored because they seemed too unlikely. Only after multiple detections from independent telescopes did anyone take them seriously. The pattern only becomes clear when you accumulate enough examples to rule out random noise. But if you are dismissing examples as noise, you never accumulate enough to see the pattern. Unknown unknowns are the hardest problem in science. You cannot search for something if you do not know it exists. You cannot design instruments to detect signals you haven't imagined. Every major discovery of a new type of astronomical object was preceded by stumbling across it accidentally while looking for something else. Pulsars were discovered while studying interplanetary scintillation. The cosmic microwave background radiation was discovered while testing a radio antenna for satellite communication. This means our understanding of the universe is biased toward the things our instruments happen to detect. We have built telescopes optimized for certain wavelengths, certain timescales, and certain types of events. Anything outside those parameters is invisible to us, not because it doesn't exist, but because we are not looking for it in the right way. Observational blind spots exist in every survey. Satellites in low Earth orbit cannot see through the planet. Ground-based telescopes cannot see through clouds or the atmosphere at certain wavelengths. Radio telescopes are drowned out by human-generated interference near cities. The galactic plane is so crowded with stars that finding individual objects is difficult. The Milky Way's dust obscures optical light from the galaxy's far side. We monitor a tiny fraction of the sky at any given time. And even that monitoring is constrained by available funding, telescope time, and human attention. Detection lag is another issue. From the moment a signal arrives to the moment someone realizes it is significant can take years. Data gets archived. Algorithms process it later. Patterns emerge only after multiple observations. The famous WOW signal from 1977 is still unexplained, partly because it was detected in archived data and was never observed again. By the time someone realized it was unusual, the moment had passed. We cannot go back and look again. We can only speculate. Cosmic near misses are events we detected only because we got lucky. If timing had been slightly different, if our instruments hadn't been pointed in that direction, if the signal had been weaker, we would have missed it entirely. And we do not know how many we have already missed. For every fast radio burst we have detected, how many occurred when no telescope was watching? For every gravitational wave event we caught, how many merged before LIGO was turned on? Framing ignorance as dangerous isn't about creating paranoia. It is about acknowledging limitations. We assume that if something important happens in the cosmos, we will detect it. But that assumption is wrong. Most of what happens unobserved. And if an intelligence wanted to communicate without being obvious, they could easily exploit our blind spots. They could send signals in wavelengths we do not monitor. They could use timescales we are not watching. They could embed messages in natural-looking phenomena that we dismiss as astrophysical noise. This reinforces the caution necessary when interpreting objects like 3I Atlas. We are seeing one moment in its journey. captured by instruments designed to answer specific questions. Anything outside those parameters might be invisible to us. The message might already be there. We just do not have the right receiver. Artificial intelligence has transformed how we search for anomalies in astronomical data. Machine learning algorithms can process terabytes of information faster than human astronomers can review it. They flag unusual patterns, categorize objects, and prioritize targets for follow-up observation. This has accelerated discovery rates across every field of astronomy, but it has also introduced new failure modes that could cause us to miss exactly what we are looking for. AI anomaly detection works by learning what normal looks like. You feed the algorithm training data containing examples of known phenomena: stars, galaxies, comets, asteroids, instrumental artifacts, cosmic rays, satellite trails. The AI builds a statistical model of normality. Then it scans new data and flags anything that deviates significantly from that model. The further something deviates, the higher its anomaly score. Simple in concept, complicated in practice. Bias in training data determines what the AI considers normal. If your training set contains mostly nearby, bright objects, the algorithm might flag distant, faint objects as anomalies even if they are common. If you trained it only on data from one telescope, it might misinterpret data from another telescope's instrument signature as unusual. If your training set includes very few examples of rare phenomena, the AI learns that those phenomena are noise rather than signal. Every AI inherits the assumptions and limitations of its training process. The Breakthrough Listen project uses machine learning to search for technosignatures in radio telescope data. They have collected petabytes of observations from thousands of stars. Humans cannot review that much data manually. So, they train algorithms to identify narrowband signals that do not match known interference sources. The problem is that interference sources are diverse and constantly changing. New satellites launch. New electronics come online. Radio regulations change. The algorithm has to distinguish between artificial signals from space and artificial signals from Earth. It is not always clear which is which. False positives versus false negatives is the fundamental trade-off. If you set the anomaly threshold too low, you flag everything unusual and drown in false alarms. Astronomers waste time investigating phenomena that turn out to be instrumental glitches or cataloging errors. If you set the threshold too high, you miss real discoveries. The signal you are looking for might be just below your cutoff, dismissed as noise because it wasn't weird enough to trigger a review. Most systems err on the side of false positives because missing something important is considered worse than wasting time on noise. But this leads to alarm fatigue. After enough false alarms, researchers start assuming that flagged candidates are probably nothing. They review them less carefully. And that is when you miss the real signal. It gets lumped in with everything else and dismissed without proper analysis. Automation trust is a psychological issue. When an AI flags something as significant, humans tend to believe it. The logic is, the algorithm wouldn't flag it if it wasn't important. Except algorithms make mistakes. They have blind spots. They misclassify things. But there is a cognitive bias where we treat computer output as more reliable than human judgment. Conversely, when an AI doesn't flag something, humans assume it is unimportant, but the AI is just following rules. It doesn't have intuition. It doesn't have context. It cannot recognize something it wasn't trained to find. Over-relying on automation means you stop checking the things the AI ignored. You trust that if something were significant, it would have been flagged. But what if the signal is subtle? What if it is embedded in data that looks normal by every metric the AI was trained on? What if the intelligence sending it understood exactly how our detection systems work and crafted the message to slip through unnoticed? You would never find it. Not because you weren't looking, but because your AI was trained to ignore it. Human oversight limits are about cognitive bandwidth. A human can carefully review maybe a few hundred candidates per day. An AI can process millions. This speed advantage is essential for modern astronomy. But it creates a bottleneck at the verification stage. We are generating candidates faster than we can verify them. Most flagged candidates never get human review unless they meet specific, pre-programmed criteria. This means the AI's initial judgment filters out most of the data before a human astronomer ever sees it. You are trusting the AI to make the first cut. And first cuts are where things get lost. Feedback loops develop over time. When an AI flags something and humans confirm it is real, that information goes back into the training data. The AI gets better at finding similar things, but it also gets narrower. It learns to find what humans confirm, which reinforces existing biases. If humans keep confirming one type of anomaly, the AI learns to prioritize that type and might start ignoring others. The system optimizes for past successes, which makes it worse at finding future surprises. Misinterpretation consequences in astronomy are usually academic. If you misclassify a galaxy as a star, you publish a correction and move on. Careers aren't ruined over misidentifications, but misinterpretation of potential technosignatures has different stakes. If you dismiss a real signal as instrumental noise, you miss first contact. Humanity's biggest question remains unanswered because an algorithm made a categorization error. Conversely, if you misidentify natural phenomena as artificial, you cause false alarms, institutional embarrassment, and credibility damage that makes future claims harder to believe. The 1967 pulsar discovery almost didn't happen because the signal looked too artificial. It was so regular that researchers initially thought it was human-made interference. They labeled it LGM-1 Little Green Men. Only after finding more pulsars with similar properties did they realize it was natural. But imagine if they had stopped there. If they had dismissed it as interference and moved on. We would have missed pulsars entirely until someone else stumbled across them years later. Connecting this to message misreading is where it gets existential. If an intelligence sends a warning and we misinterpret it as natural phenomena, we miss the warning. We continue the behavior that prompted the warning. We stay loud. We stay visible. We stay vulnerable. If they send a signal designed to be ambiguous, and our AI categorizes it as noise, we never investigate. The message gets lost not because we weren't listening, but because we didn't recognize what we were hearing. Framing AI as an amplifier, not an oracle, is the responsible position. Artificial intelligence makes us better at finding patterns. It extends our capabilities. It processes data at scales impossible for humans. But it doesn't make us infallible. It doesn't replace judgment. And when the stakes involve existential questions about our place in the cosmos, about whether we are being watched, or warned, or hunted, relying too heavily on automation is a gamble we might not win. The irony is that we are using artificial intelligence to search for artificial intelligence. We are trusting algorithms to recognize minds that might think nothing like algorithms. We are assuming that whatever is out there will announce itself in ways our systems are designed to detect. But what if they don't? What if the message is already in our data, filed under noise, waiting for someone to look at it the right way? Recent planetary defense successes give us a false sense of security. NASA successfully diverted the asteroid Dimorphos in September 2022 using the DART mission Double Asteroid Redirection Test. A spacecraft deliberately crashed into a small asteroid moon to change its orbit. The mission worked. The impact altered Dimorphos's orbital period by over 30 minutes. Proof of concept: we can, in principle, protect ourselves from asteroid impacts. But that capability is limited. We need years of advance notice. The asteroid needs to be small enough that kinetic impactors work without fragmenting it into multiple dangerous pieces. It needs to be on a predictable trajectory that we have calculated precisely. It cannot be a comet, because comets behave unpredictably as they outgas. It cannot be coming too fast, because then we don't have time to launch an interceptor. Most cosmic threats do not meet those criteria. Contrasting known threats versus unknown ones clarifies the problem. Asteroids are known threats. We have cataloged most of the large ones. We are working on the smaller ones. We have models for impact, frequency, and potential damage. We know roughly how much warning we would get. Unknown threats are everything else. Rogue planets ejected from other stellar systems, traveling through interstellar space. Comets from the Oort cloud on long-period orbits we haven't mapped yet. Gamma-ray bursts from collapsing stars light-years away. Solar flares powerful enough to strip our atmosphere. Phenomena we haven't imagined yet because they exist outside our current physics. You cannot prepare for what you do not know exists. This is the fundamental challenge of existential risk mitigation. You can build defenses against specific threats, but general resilience is harder. How do you protect against something you cannot predict? The best answer is redundancy. Multiple planets, multiple habitats, distributed backups of civilization. But we are nowhere near that level of capability. We are still a single-planet species with all our eggs in one fragile basket. Biosignature ambiguity is a related issue in the search for life beyond Earth. When we detect oxygen in an exoplanet's atmosphere, we interpret it as potential evidence of life. Because on Earth, oxygen is produced by photosynthesis. But oxygen can be produced by non-biological processes. Photodissociation of water vapor by ultraviolet light creates oxygen without biology. Volcanic outgassing can release oxygen if the chemistry is right. Distinguishing life from mimics requires more data than we currently have for most exoplanets. This means biosignatures are hints, not proof. Suggestive, but not conclusive. And if we can misread biosignatures, we can misread technosignatures. 2. A signal that looks artificial might be natural. A pattern that looks like communication might be noise. Or worse, a phenomenon that looks natural might be artificial. The universe doesn't label things for our convenience. We have to figure it out ourselves, knowing that we might be wrong. Reflecting on the Fermi paradox again brings us full circle. Where is everyone? Maybe they are hiding. Maybe they have gone quiet. Maybe they have transcended physical form into something we cannot detect. Maybe they existed long ago and left no traces. Maybe they are coming but haven't arrived yet. Maybe they are here, but we do not recognize them. Or maybe the great filter is ahead of us, not behind us. The Great Filter hypothesis suggests that at least one step in the evolution from non-life to spacefaring civilization is extraordinarily improbable. If the filter is behind us in our past, then we are lucky to be here. And the galaxy might be full of life once it gets started. But if the filter is ahead of us in our future, then we are approaching something that kills most civilizations. Nuclear war, climate collapse, unaligned AI, nanotechnology accidents, or something we haven't thought of. Something that waits for every civilization at roughly the same technological level we are reaching now. Survival versus curiosity is the tension at the heart of this entire discussion. Curiosity drives exploration. It makes us search for answers, broadcast our presence, reach beyond our planet, build telescopes and transmitters and spacecraft. Curiosity is what makes us human, but survival might require restraint. It might require accepting that some questions are too dangerous to ask loudly, that some discoveries come with existential risks, that the universe might be less welcoming than we hoped. This isn't an argument against exploration. It is an argument for caution, for thinking through consequences before we commit to irreversible actions. We have been broadcasting for a century already. That is done. But we can choose what we do next. We can choose whether to amplify our presence or minimize it, whether to shout or whisper, whether to assume we are safe or assume we are not. Reframing silence as adaptation suggests that the great silence isn't emptiness. It is populated by civilizations that learn to survive by learning to hide. They are out there watching, listening, existing quietly in the spaces between the noise. And the reason they are not talking is that talking is how you die. They have learned something we are only beginning to consider, that in a universe where predators might exist, prey stays quiet. The final question is simple and terrible. What if survival means restraint? What if the cost of continuing to exist as a technological civilization is giving up the very thing that makes us explorers, our curiosity, our drive to reach out, our need to answer the question, are we alone? What if the answer is yes, but only because everyone else learned to shut up? And you need to do the same. 3I Atlas reaches its closest approach on December 19th. By then, we will have more data, more observations, more analysis. Debates will continue. Papers will be published. The internet will speculate. And maybe if we are very lucky, or very unlucky, we will have an answer to the question we didn't know we needed to ask. Not are we alone, but should we stay quiet? The scariest message isn't the one that declares war. It is the one that tells us we have already lost by announcing we exist. That the game was over the moment we made noise. That the universe isn't empty. It has just learned to whisper, and we are still shouting into the dark, hoping something answers. Not realizing that silence might be the only thing keeping us alive. On December 19th, maybe nothing will happen. 3I Atlas will pass. It will continue its journey out of the solar system. Years from now, it will be a footnote in astronomical catalogs. Another interstellar visitor that came and went. Another mystery we couldn't fully solve. Or maybe we will notice something. A pattern we missed before. A correlation that shouldn't exist. A message hidden in data we thought was noise, and we will have to decide what to do with that information. Whether to respond, whether to change our behavior, whether to accept that the rules we thought governed the universe are wrong. And the real rules are far more dangerous than we imagined. Either way, December 19th marks something. A date when we were forced to consider possibilities we would rather ignore. A moment when comfortable assumptions about our place in the cosmos became uncomfortable questions. A time when we had to ask ourselves, if we received the scariest message possible, would we even recognize it? And if we did recognize it, would we be brave enough to be silent?